Okay, let's talk a little bit about quantum mechanics today. We have finally arrived at 1900, so we finally made it to the 20th century. And what we're about to talk about could arguably be considered the greatest discovery of the 20th century. You could make a case for the transistor, which probably wouldn't have happened without quantum mechanics. You could make a case for the internet. I get it, but I'm a chemist, and so I'm entitled to my own opinion, I guess, and so are you. So this is kind of important stuff. We talked about Bohr's model of the hydrogen atom and how it was really, really good for hydrogen, but it just really didn't work for anything else. So I guess all that work was in vain, right? Well, not quite. Don't feel too sorry for Niels Bohr, because what we're about to talk about next, Niels Bohr had a lot to do with. So it wasn't like he came up with that and just quit. So he's okay. He'll be all right. Okay. So if someone asks me to describe quantum mechanics in two simple statements, I would say that is very difficult to do. All right, but that's exactly what I'm going to try to do right now. Is we're going to talk about the quantum mechanical model. So we had some issues with Bohr's model, and one of those issues that was kind of important was the fact that atom should collapse in less than 1 times 10 to the -8th of a second. And we know that doesn't happen because atoms are stable. They hang around for, eons instead of just collapsing. So we got to come up with some sort of a model that keeps that electron from collapsing into the nucleus somehow. And that's where a concept of something called a standing wave comes into play. Quick physics lesson here. A standing wave, you can take a rope and you can hook it up to a pole. And then you can sit there with the other end of the rope and you can kind of flick that rope. Just kind of give it a little flick there. And you can watch the waves move down the rope. Well, there's a principle in physics that if a wave hits a solid barrier, could be a wall, could be whatever that rope is attached to, the pole, the energy is reflected back and it's inverted 180 degrees in phase. So in other words, if my rope is coming and it hits the pole kind of on the upside of the amplitude, when it reflects back, it will reflect back from the downside and go back the other way. And so you have waves that are coming this way and then the reflected waves that are coming back the other way, and they're interfering with each other. And they can either interfere constructively, in other words, they can reinforce each other, or they can interfere destructively, in other words, they can cancel each other out. All right. Well, if you flick that rope with a certain frequency, what happens is the waves that are going forward exactly correspond with the waves coming back, and they reinforce each other. And what you get something called a standing wave. And essentially what it is my little rope is vibrating up and down, and it kind of makes an arc here, and it kind of makes an arc down there. And so it looks like the rope isn't moving, but it actually is. It's moving up and down very rapidly. And that only happens at a certain frequency. If you flick that rope at exactly twice the speed, then what you get is you get two standing waves. You get a little hump here, up and down, and then you get a point here where the rope is not vibrating at all. And that's where the first wave coming this way interferes with the wave that's coming back, and they completely cancel each other out. And so the rope doesn't move, and that's called a node. And then you get another little wavelet over here. So you get two little wavelets there. If you flick that rope at 3 times the original frequency, then what you get is you get 3 little wavelets. 1, 2, 3, and then of course the corresponding bottom one here. And you get 2 little nodes, places where the rope isn't moving, and so on and so forth. And that's how music works. You pluck a string on a guitar, and it's of a certain thickness and of a certain tension, and you get a standing wave between the nut and the bridge, and that corresponds to a frequency that your ears perceive as sound. And so if it's vibrating at a certain frequency, we call that A. If it's vibrating at a different frequency, we call that C. But that's it. And it's stringed instruments work that way. You're looking at compressed air in a tube if you're talking about woodwinds or brass instruments or things like that. And then you can take your finger and you can put them on a string on the guitar, and you can actually make that little string shorter. So therefore you have a different fundamental frequency there. So you can start playing notes there. And that's pretty much how music works. Works kind of like that. It's waves. Standing waves, really. Well, what does all that have to do with this? Well, what we assume is, well, we don't just assume, but it's actually, there's some experimental evidence that things, we used to think of things as either particles or waves. It's either a wave, it's either energy, or it's matter, particle. But in reality, everything has some particle-like properties and have some wave-like properties. So if you're very big and very slow, like me, you behave a lot like a particle and very little like a wave. Right? But if you're really, really tiny and moving really, really fast, those wave-like properties start to predominate, and you have to take those into account. Now, the interesting thing about a wave is you can't really pinpoint where it is. You can pinpoint where a particle is. Pretty easy to see exactly where that particle is. But a wave is kind of ghostly. It's, here and there and all over the place. And so it turns out that you can actually calculate your own wavelength. It's called the de Broglie wavelength. And it's an extremely short wavelength with a very high amplitude. In other words, the size of the wave. And so the higher the amplitude, the greater the probability you are at that spot. The lower the amplitude, the lower the probability. So in reality, there's a chance that I'm not sitting in this chair. There's a chance I'm actually over in the other room there. But it's an extremely low chance. Odds, because I behave very, very, very much like a particle and very, very little like a wave. But when you get down to the world of the electron and the quantum mechanical world, that wave-particle duality kind of takes effect. And you have to consider it. If you don't, it's at your own peril. All right? Yeah, I know, kind of weird. Okay. So that's where we got the 1, 2, 3, 4 from. Essentially, the 1, 2, 3, 4, the quantized stuff is there because of the standing wave stuff. There are only certain fundamental frequencies or wavelengths that electron can have that keeps it outside the nucleus. Just like there are certain fundamental frequencies that a string can vibrate at to get those standing waves. And so when we consider electrons as waves, that keeps that electron from collapsing into the nucleus, and we can explain it that way. Okay? All right. Well, what are some consequences of that? Well, because you can't pinpoint waves as easily as you can particles, here's the problem. You can only refer to the probability of finding an electron in a region of space. All right? In other words, you can't draw the electron as a little tiny ball. You can't pinpoint it. All you can say is there's a chance it's within this box somewhere. Okay? It gets even more depressing than that. You can't even specify the path. So in other words, you can't draw it as a little tiny ball, and you can't even draw the circular path. Okay? And that's something called the Heisenberg uncertainty principle, which essentially states it's impossible to know the position and the direction of a particle at the same time. If you try to measure one, you are less certain about the other, and vice versa. Okay, so what does all that mean anyway? Here's an illustration for you. Let's say, for example, you've got a dog sitting in the backyard. Okay, but you can't see. You're in the kitchen. Can't see the backyard. Without looking in the backyard, can you tell exactly where your dog is? Well, no, you can't, right? Unless you actually see. All right. However, if you know your dog, there are places in the backyard where he is more likely to be than others. So let's say, for example, it's noon. Okay, and you can say, since I know my dog, with a 75% chance my dog is somewhere near his supper dish because he always eats lunch around noon. All right. Does he have to be there? No, he doesn't have to be there. He could be, laying on top of his doghouse, taking a nap like Snoopy, something like that. Or he could be over here, underneath the tree, taking a nap. Or he could be chewing on his ball over here, or checking on the bone he buried, or something like that. He could be anywhere in the yard. But there are places where he is more likely to be. All right. Let's say, for example, I've got my supper dish, and we said there was a 75% chance he was somewhere around the supper dish. Is there a finite possibility he is somewhere within that 1 square meter space in your backyard? Yeah, there's a chance. Is it likely? No. So, basically what we're saying is this. The more you try to narrow down the space, the more you have fixed the position of the little dog. But I could say there's a 99% chance that the dog is somewhere in the backyard. There's that 1% chance that he's dug under the fence, he's out here chasing a cat, right? It's always that chance. You ever have a dog that's a digger? Those are hard to stop. All right? I'm 99% sure he's in my backyard, but what's the problem? I haven't really narrowed it down. See, he could be anywhere here. The more I try to narrow it down, the lower the probability that he's actually within the little square space that I've made. The more I widen it out, the more sure he's there. But again, the problem is I've narrowed it down less. And that's the Heisenberg uncertainty principle. You can't know one and the other at the same time. All right? Well, let's say you did. Hypothetically, let's say I know that my dog is at his supper dish. I know it, 100%. How'd he get there? Well, without looking at the dog, you don't know. He could have been taking a nap and came straight over to his supper dish. Or maybe he was over here and he was chewing on his ball, and then he came over here and checked on the bone, make sure that was buried, and kind of, went around the tree a few times, and then came back over to your supper dish like that. Maybe barked at the cat and came back over here. You don't really know unless you see. And that's kind of where we are in quantum mechanics. We cannot specify the electron as a little tiny ball. We don't know exactly where the electron is. All we can do is specify a region of space where that electron could be. The more we narrow it down, the less sure we are. The more we widen it out, the more sure we are, but then it becomes a point of it's not even worth the trouble. There's a 100% chance the electron is somewhere in the universe. Does that help me? That doesn't help me at all. See? So you want to narrow it down somewhat. You also can't draw the little circle. You can't say the electron's moving from here to there because you can't see it, and you can't specify the path. All you can do is specify the region of space, just like our little dog here. Does that make sense? Okay. Well, that's one thing. That's the Heisenberg uncertainty principle. So what's the second principle here? Well, 4 quantum numbers are required to describe the energy of an electron completely in all atoms. Okay, and this is something called the Pauli exclusion principle. 4 quantum numbers are required to describe the energy of an electron completely in all atoms. All right. You can think of the 4 quantum numbers as kind of like the Social Security number for an electron. So let's say, for example, I have my sodium atom, and I know that neutral sodium atom has 11 electrons. Well, each of those 11 electrons has its own distinct set of 4 quantum numbers. The first one might be the same for 2 of them. You might even have the first 2 the same for 2 different electrons. 3 of them might be the same, but I guarantee you that 4th one's going to be different. It's like everybody in your class. Each one of you in your class has your own student number. You might have the first digit the same, and even the first 2 or 3, but there's no one else at Midland College that has exactly the same student number as you. That is unique to you. Well, that's what the Pauli exclusion principle says. It requires 4 electrons to describe the energy of every electron in that atom completely. All right? So where do you think we're going next? Yeah, we're going to talk about the 4 quantum numbers. Okay? And finally, we have gotten to the point, now we're going to talk about electronic structure. How are the electrons arranged around that nucleus? So we made it. Just took, 3 videos to get there. Okay? Now, as we go through this, what I'm going to give you here, it's going to look like a bunch of rules, all right, that don't seem to make any sense. And the reason why is it is kind of a bunch of rules. A lot of this stuff comes from some very complicated mathematical equations that you really don't want to deal with right now. Keep in mind that what I'm giving you here is I'm giving you the answers. I'm not giving you the problem. All right, so when I say n can be 1, 2, 3, 4, 5, so on and so forth, it's like we looked in the back of the book and went to problem number 38 and it said 3.82 grams. You know, that doesn't tell you how to do the problem, that's just the answer. All right, so at this point, you're just going to have to kind of take it on faith that someone did the math for you and came up with the answer. So a lot of these rules you're just going to have to memorize. Just like you would have to memorize the answers in the back of the book if you had a desire to do that. The other problem here is this is very abstract. And there's not a lot of concreteness to kind of hold on to anchor to. I will do my best to make some analogies that will allow you to kind of correlate what's happening down in the quantum mechanical world. The world is very tiny, although actually the same things are happening up here. The effects are just too small for you to be able to see what's going on. And our world up here. Keep in mind the analogies I give you are not perfect. Sometimes there just isn't a perfect analogy. But I'm doing the best I can, and I want you to be able to understand this at least somewhat, hopefully better than me. There was a famous scientist that once said, if you think you know everything there is to know about quantum mechanics, you don't know quantum mechanics. So even the experts, we get numbers out of these equations sometimes, and we don't know what that actually physically corresponds to. So it's difficult to understand. But I will do the very best I can to help you understand it as much as you can. And if you really want to learn more about this, you need to take some math. Lots and lots and lots of math. But it's kind of fascinating. Okay? All right. Well, all that being said, let's talk about your 4 quantum numbers. So let's start with number 1. The first quantum number is given by the letter N, and that is the energy level or the energy shell. I have seen books call it both. I typically prefer to say energy level, so you'll probably see me accidentally do that. Your book is calling it the energy shell, so, well, there you go, energy shell. The allowed values for N, what N can be 1, 2, 3, 4, all the way up to infinity. So in other words, an electron can be in the first energy shell, the second energy shell, the third energy shell, and so on and so forth, but not the 2.5. Okay? Does that look familiar to you? Have you ever seen anything that looks like that before? Yeah, I think you have. There it is. See, back here in Bohr's theory of the hydrogen atom, see? So, yeah, that's where it came from. Yeah, a lot of this stuff was actually kind of feathered on by Niels Bohr here. Okay? The value for N is the main factor that determines the energy of an electron and, correspondingly, its distance from the nucleus. So in other words, if an electron is in a low energy shell, that means it is relatively close to the nucleus. It spends its average time close to the nucleus, and that means it's low in energy. All right. You can think of energy shells as like parking lots for cars. You got Midland College here. We got all sorts of parking lots. You got one over by the Shap Center. You got one over here by the bookstore. You got one over here at Fox Science Building. You got the science faculty one. It's just parking lots all over the place. And all those parking lots are varying distances from varying buildings, and some of them are large and hold a lot of cars, and some of them are really small and hold very few cars. Okay, well, you can think of N or energy shells as kind of like parking lots for electrons, although electrons don't pull into a space and stop. All right? The value for N is the main factor that determines the energy of an electron. Electrons in the first energy level shell are lower in energy than the electrons in the second energy shell, which are lower in energy than the third, and generally so on and so on and so on and so forth. The maximum capacity of any energy shell is given by this handy-dandy little formula, 2n squared. So all you got to do is plug in to that little formula, and that tells you the maximum number of electrons that that energy shell can hold. So the first energy shell, 1 squared is 1 times 2 is, I can fit 2 electrons in the first energy shell. 2 squared is 4. 4 times 2 is 8, so I can fit 8 electrons in the second energy shell. 3 squared is 9. 9 times 2 is 18, so 18 electrons in the third energy shell. 4 squared is what, 16? 16 times 2, 32 electrons in the fourth energy shell, and so on and so on and so forth. Do you see a trend here? Well, notice as I get out further from the nucleus, I can fit more and more electrons in my shell. My parking lots are getting bigger, which makes sense because if you're really close to the nucleus, there's not a lot of space there. And so your electrons start repelling each other if you get them too close. But the further out you go, the more space you have out here, and so you can fit more electrons in there before the repulsion starts to get too bad. All right? But that's your formula, the 2n squared. Let's say, for example, you've got your parking lot out here at the back of the Fox building. Okay, that parking lot is divided into sections. If you think about it, there's yellow spaces, and there's white spaces, and there's handicap spaces, right? Okay, what are the yellow spaces for? Teachers. Teachers park in the yellow spaces. What are the white spaces for? Students. Students park in the white spaces. Do students park in the yellow spaces? No, students don't park in the yellow spaces. Teachers park in the yellow spaces. Did everybody get that? Hey, I don't get paid a lot of money. All I get's a space. So, don't park in my space, please. All right? If you had a choice, where would you rather park? Would you rather park in a handicap space, a yellow space, or a white space? Well, probably a yellow space just to spot me now, right? Well, you'd probably rather park in a handicap space, right? Well, why would you want to do that? Well, because it's closer to the building, right? Right. Well, it turns out that energy shells are divided into subshells, or sublevels. And that's your second quantum number, and that's given by the letter L. And L can be 0, 1, 2, 3, up to n minus 1. So the value for n determines the allowed values for L. All right? So within each parking lot, with each energy shell, there are certain places, subshells, okay? And some are more advantageous than others. For example, the handicap spaces are closer to the building than the yellow spaces. And the yellow spaces are closer to the building than the white spaces. Is every yellow space closer to the building than every white space? No, there are some white spaces that are closer to the building than some yellow spaces. But is your average yellow space closer to the building than your average white space? Yes. Okay, and that's what's going on here. All right? The lowest allowed value for L is 0. All right, so let's say, for example, we're talking about the first energy shell. What are the allowed values for L? Well, up to n minus 1, 1 minus 1 is 0. So from 0 to 0, I guess that means 0. L equals 0. Now, that doesn't mean there are no sublevels. What that means is there's one sublevel, and it has a value of L equals 0. All right. In other words, the first energy shell has no subdivisions. The subdivision is the entire energy shell, which makes sense because we're talking about 2 electrons. If you had a parking lot that held 2 cars, how many sections do you really need? You really don't need any, right? There's only 2 cars. Surely you can find your car in there. All right? When n is equal to 2, what are the allowed values for L? Well, 0 up to n minus 1. 2 minus 1 is 1. So therefore, L could be equal to 0, or L could be equal to 1. In other words, there are 2 sublevels in that second energy shell. One with the value of 0, L equals 0, one with the value of L equals 1. So imagine a parking lot with yellow spaces and white spaces. That's what it would kind of be. All right. When L is equal to 3, the allowed values are 0, 1, up to n minus 1. So 3 minus 1 is 2. So 0, 1, and 2. So that's kind of like our handicap spaces, my yellow spaces, and the white spaces here. 3 sublevels in the third energy level or energy shell. All right, notice that as we go up, we get more sublevels. In fact, notice as we go up, the number of sublevels is equal to whatever energy level I'm in here. So in the 5,000th energy shell, how many sublevels are there? Well, there are 5,000 of them, and they go from 0 up to 4,999 n minus 1. Okay? Okay, so those two are what we call the first two quantum numbers. Now, since they're numbers, sometimes we try to keep from getting them all confused. And so we give the first quantum number a number, and we give the second quantum number a letter. And that way we can tell the difference between them really easily. So these are your sublevel designations. When L is equal to 0, we call that an S sublevel. Okay, that actually stands for sharp, and it goes back to the old spectroscopy stuff we were talking about. There was a particular sharp line on a spectrum, and it was some electron that was hopping down from an S sublevel, and so they called it S. That's where it came from. Doesn't matter if it's what we call a 1S, a 2S, or a 3S. In other words, third energy level, S sublevel. All S sublevels hold 2 electrons, always. So when you see S, maximum capacity there is 2. Okay? When L is equal to 1, we call that a P sublevel. P stands for principal. There was a very bright line on a particular atomic spectrum, and that's where that kind of came from. All P sublevels hold a maximum of 6 electrons. Doesn't matter if it's a 3P, a 4P, a 5P, a 6,000P. 6 electrons is the maximum they hold. Okay? When L is equal to 2, we call that a D sublevel. It stands for dim or diffuse. Very weak line on a particular spectrum. That's where that came from. D sublevels hold 10 electrons. Are you noticing a pattern here? As I keep going up, what's happening to my capacity? It's going up by what? It's going up by 4 each time. Do you see that? 2, 6, 10. Okay? L equals 3, that's an F sublevel. That stands for fundamental. How many electrons do you think I can fit in an F sublevel? Well, 14. See, that's 4 more there. Okay? And we could keep going if you wanted to. We go to G, we go to H. They skip I and J for some reason. Probably because those are your eigenvalue normal vectors there. And so they skip I and J, they go to K, and then L, and then M, and then N, and so on and so forth. And they just kind of go alphabetically after that. That's kind of how your sublevels work. So technically, if your energy shells can go to infinity, then your sublevels can also go to infinity. Technically, infinity minus 1, I suppose. But there is a practical limit to how high you need to go, and we'll talk about what that is and why a little bit later. Okay. All right. So we got our parking lot. We've got it divided into sections here. You got your yellow section, you got your white section, and so on and so forth. Well, that yellow section out there in the parking lot, if you look at it, is composed of 2 different rows. So one of those rows is probably closer to building than the other, right? Your white section out there, large as it may be, is also composed of different rows. Well, your row there is the third quantum number. Okay, so you have energy shells, which are divided into subshells, or sublevels, either way. The sublevels are actually divided into orbitals. So if you think of this as kind of a hierarchy thing, it really does help keep it straight in your head. All right? Your third quantum number is given by m sub L. This, by the way, L is your angular momentum quantum number. You just really want to know. This is your magnetic moment angular momentum quantum number, m sub L. Okay? And that's the orbital the electron is in. The allowed values for m sub L depend on the value for L, just like the allowed value for L depends on the value for N. M sub L can be anywhere from negative L up to 0 up to positive L. All right, so let's take a look at it. So when L is equal to 0, what do we call that? That's an S sublevel. Okay. How many orbitals do I have in an S sublevel? Well, anywhere from -0 up to +0, which is just 0. So the allowed value for M sub L is equal to 0. What that tells me is there's one S orbital in an S sublevel. Okay, doesn't mean there's none of them. Okay, this just means there's one of them and it has an M sub L value of 0. Okay, when L is equal to 1, that's a P sublevel. Talked about that. What are the allowed values for M sub L? Well, -1, 0, +1. See, negative L up to positive L. So there are 1, 2, 3 p orbitals in a p sublevel. Put them all together, you've made the p sublevel. When L is equal to 2, that's a d sublevel. What are the allowed values? Well, -2, -1, 0, 1, and 2. So there are 1, 2, 3, 4, 5 d orbitals in a d sublevel. And when L is equal to 3, this is as far up as we'll go for this, that's an F sublevel. M sub L could be -3, -2, -1, 0, +1, +2, +3, negative L up to positive L, 1, 2, 3, 4, 5, 6, 7 F orbitals in an F sublevel. Okay? All right. And those are your first 3 quantum numbers. So you have energy levels, which are, or sublevel, or shells, made up of sublevels. Your sublevels are made up of orbitals. So it's kind of like a parking lot, section, row. Kind of like that, sort of. Well, would you like to see the shape of the orbitals? Let's talk a little bit about that real quick. So, how do I determine what these things look like? Remember, we can't pinpoint where the electron is, but we can specify a region of space. Well, it turns out that what you can do for a wave is you can actually write an equation. For example, if I had a little sine wave, just a straight up and down little thing like that, I can actually write an equation for that, A equals sine theta. And you can take A equals sine theta and I can graph that. And I actually get my little sine wave out of that. Well, we said an electron can be a wave. Can I write an equation for an electron? Actually, you can. You can write an equation for an electron. It's a lot more complicated than A equals sine theta. And sometimes what we do is we give it this little Greek letter here. This is a Greek letter psi, capital psi here. And that's something called the wave function of the electron. And there's probably one for the hydrogen atom, the electron and the hydrogen atom, the time-independent one there. So probably in your problem somewhere, I'm sure. It's pretty nasty looking. You don't want to mess with it. Okay? The reason I'm telling you all this is because what you can do is you can take that wave function there and you can square it. Technically, you actually multiply it by its complex conjugate, but for our intents and purposes, we're going to call it squared. Okay? And if you square it, you get something called the probability function. And if you take that probability function and you graph it, what you get is you get a picture of the region of space where the electron is most likely to be. Now, normally when we draw these orbitals, which is what these are, just graphs of where the electron is most likely to be, we draw them at the 99% confidence level. In other words, we're 99% sure the electron is somewhere within this region of space. Because remember, you can only express the probability of a particle being in that particular position. Okay? And so 99% probability is what most orbitals are drawn at. So that's what I'm about to show you. Electrons are three-dimensional, just like you and me. They can move up and down, forward and back, and all sorts of stuff like that. And so the graphs I'm going to show you are actually three-dimensional graphs. All right? So where to start? Well, let's start with an s orbital. Remember the allowed value for m sub L when L is equal to 0 is just m sub L equals 0. So there's one s orbital. So essentially, if I draw you an s orbital, I have also drawn you a picture of what the entire s sublevel looks like, right? Because there's only one s orbital in a sublevel. So what does it look like anyway? An s orbital looks something like this. Okay? Imagine that my nucleus is sitting here in the center of this kind of solid sphere. So imagine something like a Nerf ball, I guess. Okay. Imagine the nucleus in the middle, and then the region of space around that is where those two electrons are most likely to be. And that's the best you can do. You can't pinpoint either one of them. You can just specify that region of space. The key is for an s orbital is it's spherical in shape. Now, when you get to a 2s, second energy shell, technically what you have is you actually have a region of space here where the electrons are most likely to be, a region of space here where the electrons are most likely to be, and technically a mathematical point right here in the middle, and that's a node. And a node is a point of zero probability. In other words, there's zero possibility the electron is somewhere within that region of space. Does that mean one of them's here and one of them's here? No, it doesn't mean that. Does it mean they're both here? Could be. I mean, it could be both here at the same time, too. How does an electron get from here to here but never pass between that point? Just does. Welcome to the world of quantum mechanics. A 3s is like three nested spheres with two nodes. And it all comes back to that standing wave stuff we talked about, where the wavelets with the little nodes. That's really it. But, and here's your radial probability. Notice it's here, and it tapers off pretty good. There's that node right there. See, there's the two nodes. That corresponds to this right here, three-dimensional wise. But really what you need to know in the grand scheme of things is an s orbital is spherical in shape. If you can remember that, you don't have to worry so much about the node thing. Just think 1s small sphere, 2s larger sphere, 3s larger sphere, because the electron is further away from the nucleus in a 3s than a 2s, so therefore higher in energy. And it turns out that within an s orbital you can put two electrons. It actually turns out any orbital always holds two electrons. Doesn't matter what type of orbital it is. So if I have one s orbital and there's two electrons in it, how many electrons can I fit in an s sublevel? Well, I can fit two electrons in an s sublevel. And I've drawn you a picture of the orbital here. That is a picture of the s sublevel. And the difference between a 1s, a 2s, a 3s is just small, larger, larger, larger still. The node thing there, but, again, size is kind of what we're looking at here. Well, that's what an s looks like. So what's next? Well, p, right? So I'll tell you what we're going to do. We're going to quit right here. We're going to continue our discussion of quantum numbers, because looking at all four at one time sometimes will tend to kind of blow your mind a little. And so there are some things in life that just need to be kind of absorbed a little bit. So see what you can do to kind of absorb that. We'll come back, we'll draw you a picture of a p orbital and a p sublevel. We'll do the d. I'll show you a picture of the f, because I really cannot draw that. It's pretty interesting looking. And then we'll move on from there. Then we got our fourth quantum number. And then we're actually going to start looking at electron configurations. So yeah, it only took me, 3 to 4 videos to make it to the 21st century. But we'll go from there. All right. So we're coming up on about 40 minutes, so I think that's probably enough for today. So we'll quit there, and I'll see you next time.